Okay, we're live. So welcome everyone to another TCS Plus talk. We're very happy to have Andrea Lincoln from UC Berkeley, who will be telling us about new techniques for proving fine-grained average case hardness. And just before we begin, let me just give credit to the rest of the organizers, which include Clement Canon, Rachel Cummings, Anindya Day, Sumegha Garg, Gautam Kamath, Ilya Rajenstein, Oded Regev, Salil Shram, Noah Stevens-Davidowitz, Tomas Vidic, and David Weiss. And I'll also mention that 2 weeks from now, we'll have Ronen Eldan from the Weizmann Institute talking to us about the KLS conjecture. And yeah, just final thing, I encourage people to unmute themselves, ask questions, and keep their camera on. And yeah, I think that's all. Andrea, please take it away.
Great. Yeah, so as mentioned, I'm Andrea, and I want to tell you guys about some new ways to prove worst case to average case lower bounds in the fine grain, like that have a fine grain complexity event. And this is joint work with Mina and Virginia. So what's the goal of this whole talk? Our hope is to understand how hard some of our favorite problems are on average, starting from plausible worst case hypotheses, specifically plausible worst case fine-grained hypotheses. And the goal is to understand what distributions these problems are hard under. Like that's sort of how we want to frame this. Like what what do we actually like? Is it the uniform distribution? Is it some other stranger distribution? Great. So what can you look forward to in this talk? Like what are we going to be doing? First, I'm going to present a framework in which we give average case hardness for all problems P, as long as they have something we call a good low degree polynomial. And I will define what that is later. Next, we describe a new type of problem. We call this a factored problem. And the factored version of a problem P is more expressive than the original problem P. However, we also have the property that the counting version of these problems is hard on average. And this is because these factored versions of the problems have good low degree polynomials. So they sort of fit into our framework. Finally, we use a combination of our framework, these factored problems and reductions to show a variety of problems hard that we care about. Notably, as an example of such a result, we give a tight, lower bound on average for the problem of counting regular expression matches. So you're given a regular expression and you're given a string. And if that regular expression is of length n and the string is of length m, you can count the number of ways that these match to each other in nm time. And if you could do polynomially better than that, you would violate a popular conjecture called Seth that I will define later. So, while we're sort of, looking at what you can look forward to in this talk, I'd like to describe what a good low degree polynomial is and what you get from having a good low degree polynomial. So a good low degree polynomial, FP, for a problem P, exists as long as it's sufficiently low degree. And here that operationalizes to little o of log n over log n. It's strongly d-part-type. So I want to be able to take the input variable space. I want to be able to partition it into d partitions. And I want each monomial in our output, in our FP, to have exactly one variable from each partition. And finally, I want that FP and P are exactly equal on 0 and inputs. And FP will be defined in a space outside of this. It's a polynomial over a large finite field, whereas P is your problem defined on input strings in binary. So if P has a good low degree polynomial, and we have some hypothesis about how long our problem takes in the worst case, then in the uniform average case, so every single bit in P, we flip a coin, IID, to decide whether it's a 0 or 1. that requires the same amount of time up to a subpolynomial factor, log n to the d specifically, as long as you have a sufficiently high success probability. Now, in the average case, when we talk about success probability, we need to sort of distinguish whether we're talking about the random coins of the algorithm or the randomness of the input. And here, I'm simply going to combine them. Like, I want to know what the success probability is given both the random coins of your algorithm and the randomness of the input. If over both the randomness of your input and the random coins of your algorithm, you have a success probability of at least 1 minus 1 over some subpolynomial, specifically log n to the d, then you have to have this like time constraint that you're roughly as hard as the worst case. So this is a worst case to average case reduction for the problem P, as long as it has a good low degree polynomial. And why would we want that, right? Why is this the goal? And the reason this is the goal is because we can use this to start from some of our favorite fine-grained hypotheses about various different problems P. We can then consider the worst case counting factored versions of them, use the framework to show that the average case of this problem is just as hard, and then finally use some reductions to show that various counting graph problems or counting string problems are hard. And I keep mentioning this counting piece because for all the problems I'm going to talk about throughout this talk, we're able to give these worst case to average case reductions and these good low degree polynomials only for their counting versions. And the non-counting version, this is like a big open problem in the area, but I just sort of want to highlight that these are going to be counting results throughout this talk. So given that this is our goal, we first need to define what some of these favorite fine-grained hypotheses are in the first place. And the reason we want to do this, of course, is because we're trying to justify the average case hardness from some plausible worst case hypothesis. So here are the sort of 3 core hypotheses of fine-grained complexity. The first is about the K-SAT problem, where you're given a Boolean formula in conjunctive normal form where the clauses are of size K. And we want to return true if there's an assignment that satisfies the formula and false otherwise. And there's a hypothesis about the running time of this called the strong exponential time hypothesis, SETH. And it states that K-SAT requires 2 to the n times 1 minus little o of 1 time. Next, we have the 3-sum problem, where you're given a list L of n numbers, and we want to know if there are 3 numbers, A, B, and C, that sum to 0. And the hypothesis is that this requires n squared minus little o of 1 time. And finally, we've got all pair shortest paths, a favorite in algorithms classes. We're given a graph with n nodes and weighted edges. We want to know what the shortest path lengths between all pairs of nodes in the graph are. And this is hypothesized to require n cubed minus little o of 1 time. And something to note for all of these is we have algorithms that achieve an upper bound, above this sort of tightly, up to some subconstant factor in the exponent. So this little o of 1 is sort of suppressing, in the case of 3-sum and all pair shortest paths, subpolynomial factors, and in the case of Seth, sub-exponential factors. And throughout the talk, we're sort of going to be doing this thing where we ignore things that are subconstants in the exponent. Great. So the actual focus of this talk is going to be on 2 problems that are hard given those core hypotheses, but aren't those core problems. Specifically, the orthogonal vectors problem, where you're given a list of n vectors. There's 0, 1 vectors, and their length is roughly log n. They're actually like omega log n, but you can sort of think of them as being log n for the purpose of this talk. And we want to know if there are u and v such that they dot product to 0. And note over 0, 1 vectors, this simply means in each location, we want at least one of the vectors to have a 0. And the hypothesis is that this requires n squared time, roughly, up to subpolynomial factors. And the fun fact is that this is implied by Seth. Next, we have the 0 k-clique problem, where you're given a dense graph with weighted edges, and we want to return true if there's a k-clique whose edges sum to 0. So that is the k choose 2 edges in this clique. We want to look at all the weights, we want to sum over them, and we're looking for values where that sum is 0. And the hypothesis is that this requires n to the k minus little o of 1 time. And something I want to note about both of these problems is that these hypotheses are roughly that it takes as long as the naive algorithm, right? For zero k-clique, we can simply check all possible k-cliques, sum over the numbers, and check whether or not it equals 0, and you can do that in n to the k time. And for orthogonal vectors, you can simply take all pairs of vectors, dot product them, and check whether or not that in fact equals 0. And the fun fact for zero k-clique is that in the case of k equals 3, the 0 3-clique problem, also called the zero triangle problem, the hypothesis that it requires n cubed time is implied by both 3-sum and all pairs shortest paths. So, that's the set of hypotheses we're working with. What's an initial goal you might have? Oh, hello, I see a raised hand.
Yeah, can you hear me?
Yeah, I can hear you.
Oh, okay. So I was wondering if so here you are saying that like every k-clique and you want to see if the sum is 0. If just finding a k-clique, like if it has a k-clique or not, what can be said about that problem? Is that also, does it take n to the k minus o of one time?
There's a faster algorithm for the generic k-clique problem. It runs in roughly n to the k times omega over 3, where omega in this context is the matrix multiplication constant. Confusing, of course, because it means lots of things in different contexts. But roughly for triangle finding, you can use matrix multiplication to do that. And for larger k, you can split your, especially if k is a multiple of 3, you can split your sets of nodes and then create this very large graph where every group of k nodes is a sort of node in your new graph, and then look for triangles in this new graph. And that's how you achieve this n to the omega k over 3.
Oh, thanks.
Yeah, for sure. Great. So, what might a goal be if you're trying to get worst case to average case reductions from these fine-grained complexity problems? Well, you might hope to just find something, right? Like be able to prove that there are interesting problems that are hard on average. And it turns out in this work of Ball, Rosen, Sabin, and Vadasuvan in 2017, they were able to give this reduction where they were able to show that from the worst case hardness of orthogonal vectors, there's some particular function, FOV, which is a function over a finite field, which is hard to compute on average. And similarly, they're able to show for zero k-clique that there's some function f0 k-clique that's hard to compute on average. So this is all great news. But now we can ask some questions like, okay, what is FOV? And I mentioned it's a polynomial over a finite field. Furthermore, it happens to be the case that on the 0, 1 inputs, the counting version of OV, where you're asking for all the witnesses, gives the exact same output as this function, FOV. But for larger values, like this is a function over a large finite field, in its average case, it's getting lots of inputs of 17 or log n for various input values. And it doesn't have any clear meaning or correlation back to the original orthogonal vectors problem in that case. And the reason this is an issue is that, how would we show something like average case orthogonal vectors being hard, or a graph problem, or a string processing question being hard? And a question we can ask is okay, can we get a self-reduction starting from a problem we care about in the worst case back to itself in the average case? And the answer is yes. And I want to sort of talk a little bit about the case of clique. So starting from this BRSV paper, where they show this general technique, Goldreich, Rothblum build on that by giving a polynomial specifically for the k-clique problem. So you can build a polynomial f-clique that counts the number of cliques in a graph. And from there, they sort of note that their polynomial happens to have the property that it sort of looks like the multi-edge version of the k-clique problem. So if you imagine you can have any number of edges between two nodes, between 0 and log n, and you pick a random number of edges that you're having between these two nodes, and and now you're counting the number of cliques in this random graph. That problem can be shown to be hard via these methods. And from there, Goldreich, Rothblum, generate a gadgety reduction that shows some average case distribution of the k-clique problem being hard, the counting k-clique problem being hard specifically, from this multi-edge version. However, Bois and Dessart et al. In 2019 do something different. They sort of go from this f-clique polynomial, and they note that it has various properties where they can roughly make lots of calls to f-clique on random looking 0-1 inputs in order to solve a version of f-clique where it's over this large finite field instead. And as a result, they're able to show that in the uniform average case of graphs, Erdos-Renyi graphs, so every edge exists or doesn't exist with probability half IID, the problem of worst case k-clique and average case k-clique are the same, as long as you have a sufficiently high success probability, which in this case is like a polylog, 1 minus 1 over a polylog. And the thing I want to claim is that they're able to get back to 0, 1 to the n, and it's not really about clique. So what is it about? First, we insist that f is the sum of monomials, all of degree d. Next, we insist that f is d-partite. Once again, that we want to be able to split our variable space into d partitions such that every monomial of f has exactly one entry from each of these partitions. We want d to not be too big because our overhead is going to be exponential in d in the end. And we want the output of f and p to be the same on 0, 1 to the n. And you can formalize this into our definition of good low degree polynomials. So it turns out what we need for degree d is that it's little o of log n over log n. We need that it's strongly d-partite. Once again, this you partition your variables. Each monomial is formed by taking exactly one variable from each partition. And finally, we ask that f, p, and p have the exact same output on 0, 1 to the n. And if all of this is true, if p has a good low degree polynomial, and we have some belief about how hard this problem p is in the worst case, then it should be that hard up to a factor of log n to the d on average, as long as it has a sufficiently high success probability of 1 minus 1 over log n to the d. And what's going on under the hood, like where are these log n to d's coming from? It's coming from the fact that we're actually going to spin up like roughly log n to the d instances of 0, 1. We're going to sort of generate an average case FP value over a large finite field. And in order to solve this FP over a large finite field, we're going to spin up like log n to the d instances of FP over 0, 1 on average. And we're going to convert that back to P. And then you can union bound over these as long as they have a sufficiently high success probability, but that's where this overhead is coming from. Now, if you don't want to have to think about this log n to the d, you want to just sort of brush it under the rug, the convenient thing about our restriction on the degree is that the worst case and average case running times are the same up to a subpolynomial factor. So you can simply sort of ignore those as long as you're comfortable ignoring subpolynomial factors. And additionally, we can say that any success probability of the form 1 minus 1 over n to the epsilon for any small constant epsilon, so 1 minus 1 over n to the 0.0001, is certainly higher than any 1 minus 1 over some potentially large subpolynomial. So if you like, you can sort of think of this as being the probabilities throughout the rest of the talk, and the overhead being simply some small subpolynomial. In fact, for many of our problems, we're able to get the degree of d to be any super constant function. So just omega 1, any function that's omega 1 is sufficient for us. And so we can do better than what's listed here, but this is sort of sufficient. And so we can sort of brush under the rug exactly what our values are to not have to worry about that too much. So at a high level, like what's happening in this reduction? Like where are these various constraints coming from, right? The degree of d is coming from the fact that we have this exponential overhead in d. The strong d-partiteness is necessary for this step where we're able to turn these large finite field values back into 0, 1 values. And this insistence that f, p, and p be equal on 0, 1 inputs is so that we can do 2 steps. We want to be able to turn p into f, and we want to be able to turn f back into p in order to get a worst case to average case reduction for p itself, while using fp as sort of an interstitial mass to get this reduction to work. So now, important question, what can we even do with this, right? Like, why do we care about having good low degree polynomials? So first, let me tell you the bad news. The bad news is that the polynomials for orthogonal vectors and 0-3 clique previously described by Ball et al. In BRS v17 are too high degree. And in fact, there's good reason to believe that you shouldn't be able to find a good low degree polynomial for them. So that's the bad news. Let's get to some good news. First, we can generalize the result of BBB19, Bondasar et al., to any subgraph, not just cliques. So counting any subgraph over an Erdős-Rényi graph is just as hard in the average case as it is in the worst case. But we can do more than that. We can take, orthogonal vectors in 0-3 clique, which we care about a lot, and we can make a sort of harder version of these problems that, while simultaneously harder and more expressive, actually has a lower degree representation. And as a result, they have good low degree polynomials. So that's what factored problems are. So, how do we get these low degree polynomials? Factored problems. In order to explain what these factored problems are and explain the distribution over which they're hard, I'm going to primarily focus on the case of factored OV. And to do so, I'm going to remind ourselves of the definition of OV again. So we're given n vectors, they're 0, 1, and I want to return true if they dot product is 0. And you can think of their length, once again, it's anything that's like omega of log n, so a little bit larger than log n, but you can sort of think of them as being log n in length for our purposes. So factored OV, instead of being defined over vectors, is defined over factored vectors. What a surprise. Factored vectors are formed by taking G sets of B-length strings. And you can think of a factored vector as representing all vectors that can be formed by taking one string from each of its G sets and concatenating them together. And there's an ordering over our sets. We have set 1, set 2, set 3. So concatenating in that order. So notably here, U is sort of representing a compression on 4 different strings. And V is representing a compression over 6 different strings. And W, which has an empty set as its first set, is representing a compression over 0 strings. So not in fact a compression at all. And the big picture idea here is we're representing these extremely correlated, large, potentially very large sets of strings in this convenient compression, assuming you have relatively dense sets. But we have this pretty strong condition about how these various strings relate to each other, notably that you contain every single possible string that is formed by taking one element from each set. So now I'm going to give the formal definition of what the count of factored OV is. And I'll try and work through it slowly to make sure that we understand all the different parts. So you're given a list of n factored vectors, which once again have G sets, each of B-length strings. And we're going to say that Vj is the jth set of the factored vector V. We're going to define this output of the count of a factored vector OV instance as a sum over for all factored vector pairs U and V, this circ operator over U and V. And the circ operator is going to be defined as the multiplication over all the sets of the sum of all strings C in U and all strings E in V that correspond, if you sort of interpret them as vectors, to vectors that dot product to 0. And I'm using this sort of bracket notation with a true or false statement inside to mean that I want that to be a 1 if it's true and a 0 if it's false. So the intuition you should have here is that if you wrote out all the factored vectors represented by U and V, this U circ V operator is just counting how many pairs have a dot product of 0 in this uncompressed version. And this representation is both a faster way to compute it and will later lend itself to a low degree polynomial representation. So let's work through an example of why these are the same. So we can start by looking at U and V and counting up how many pairs in their first set have a dot product of 0. And there are these 4 pairs that dot product to 0. And in their second set, we can similarly count out how many pairs dot product to 0. And then we can say that U circ V is, 4 times 2 is 8. Alternatively, we can sort of imagine writing out all 4 vectors that U represents, all 6 vectors, that V represents. And then, counting how many of these pairs are orthogonal. And I'm not going to draw out all the lines. And the reason that these correspond to each other is, imagine, for example, picking one pair from set 1, let's say the purple pair, and one pair from set 2, let's say the blue pair. And this corresponds to one pair of strings in our output, and these will have a dot product of 0. So consider, the string, the purple pair and blue pair correspond to the string for U of 0, 1, 0, 0, 1, 0, and correspond to the string for V of 0, 0, 0, 1, 0, 1. And every pair that has a dot product of 0 in our output corresponds to exactly one pair that has a dot product of 0 in this other representation, and it's a one-to-one correspondence. We're simply, forming all possible 0 dot product pairs by considering all possible concatenations of first halves and second halves that work. And more generically, when you have G being larger, of all GY splits that work. And to sort of continue building this intuition that we're talking about sets here, I'm just going to work through this sort of trivial example of the empty set, where the number of pairs that W has that have a dot product of 0 with any of its friends is, of course, 0 because it's the empty set. So the circ operator returns 0. And the set of all W vectors represented is the empty set. So, great, all our counts are matching up. So these empty sets are a little bit trivial, and really I just sort of want to highlight that this is some particular representation, potentially strange representation, but just some particular representation of these numbers. So the next thing I want to talk about is what the counting version of factored 0 triangle looks like. And I want to do this to highlight some of the ways that this factored problem can be generalized, and also because we're going to use factored 0 triangle a little later in the talk. So you're given a graph, and instead of having each edge tagged with a weight, as you might normally, you're instead going to tag each edge with a factored vector. And once again, we're going to say that Vj is the jth set of the factored vector V. And now, we have these B-length strings. I want us to interpret those as numbers between 0 and 2 to the B, as opposed to interpreting them as vectors, as we did before. And we're going to sort of, see what happens here. Our output is, once again, going to be a sum over all possible choices. In this case, these are all possible choices of triangles in the graph. And I want the U, V, and W that corresponds to the tagged factored vectors to the edges. So, this is much like with 0 triangle, where we were previously going to, look at all triangles and then check whether or not the edges sum to 0. Here, we're going to be checking whether the factored vectors sum to 0 in some sense. And so we're going to define a new circ operator here, little circ, and it's going to be over 3 values. And once again, we're going to be multiplying over all the different sets. The sum of all possible C from U, E from V, and H from W, where C plus E plus H is equal to 0 mod 2 to the B. And once again, this bracket notation is a statement of if it's true, it's a 1, and if it's a 0, it's not. So once again, you can sort of think of this as if you were to write out all the factored vectors, ignoring carries, which we can do for reasons I'll sort of brush under the rug, but ignoring carries, this is just asking whether or not these numbers sum to 0. If you uncompressed all your values. And the thing I want to note is that we can generalize this sort of notion of a factored vector problem to be not just over, two factored vector inputs. We can have, functions over many different things, right? We had 2 before, we have 3 here, and in general, you can do K. And there's some notion of generalization of KOV, and we can have factored KOV. We've discussed previously the notion of a, zero K-clique problem, and you can generalize this to the zero K-clique problem. Further, I want to note that the function we were sort of looking at in the internals here varied, right? Like previously we were talking about, orthogonality of 2 vectors, and here we're checking whether or not a sum is equal to 0. And you could imagine having any potential function in here. Like you could have, gamma over CE and H, and just, ask whether some function, arbitrary function gamma returns 0 or 1. And a fun fact about factored problems is they're sufficiently expressive that this factored 0 triangle problem, in fact, solves the problem of, factored gamma triangle. If you were to plug gamma in here, instead of the question of C plus E plus H equals 0, the question of gamma equals 1 or something as the internals, you can solve this gamma version with the 0 version. There's some important sense in which both sum and the orthogonality statement are universal over all functions you could have here. And this will end up playing a role a little later, though a minor one. But there's just actually a lot of power in these factored versions of the problems. So, let's take a step back again. The whole reason we're defining these sort of complicated, strange looking problems is to get good low degree polynomials in order to have an average case for which these problems are hard. And I claim these exist, and I claim that as a result, the counting versions of factored OV and the counting version of 0-3 clique are hard on average. But let's actually take a look at what these good low degree polynomials look like. We're going to once again go back to our case of OV. So how do we represent a factored vector, right? What do we want to do here? And the answer is we're going to have G times 2 to the B bits. So I want 1 bit for every factored vector, U, for every set I between 1 and G, and for every string S of length B that could be in that set. And I want this bit XUIS to be a 1 if the string is actually in the set, and a 0 if it isn't. Given that, we can write a function in the following way. We sum over all factored vectors in our set. We multiply over all the different choices of sets. And then we sum over all strings S1 and S2 that have the property that the sort of associated representation of a vector, dot product to 0, and we multiply the value of XUIS1 and XVIS2. And note that this internal sum is much like in our previous statement where we sort of had roughly something counting how many pairs match between these 2 sets. This is in fact exactly what this is doing as well. And I'll note that much like before, we're sort of in some sense we could represent an arbitrary truth table in here. And as a proof by picture that these are the same, I'm just going to put the definition of our output and the definition of this function FOV next to each other and color code them to argue that these match up. So as you can see, the external sum and multiplication are exactly the same. And the internal sums are really just checking how many vectors exist in the set UI and VI that in fact dot product is 0. Now we can ask what is the degree of this function? Well, it's going to be 2 times G. So as long as 2 times G is a small enough degree, then we have a good low degree polynomial. And recall that we need that to be little o of log n over log n. How big do we need this value of G to be? Well, we can represent vectors in the original orthogonal vectors instance as long as G times B is larger than whatever those were. And recall that that means we just need G times B to be a little bit larger than log n. So conveniently, we can set G to be, for example, root log n, which is certainly small enough for our purposes, and achieve all our goals. So we in fact get nice good low degree polynomials for our problems. So I claimed that these problems were hard on average, but we should discuss what that distribution actually looks like, given the representation we have of our input. And the answer is that the uniform distribution for factored OV, we take every factored vector and we take every set in each factored vector, and we include each string in that set with probability of half IID. So we're just sort of flipping coins for each string that we're including in each set in each factored vector, totally independently of each other. So what does this say about the average case hardness with respect to our favorite hypotheses? So from Seth, the hypothesis about satisfiability, we have that the average case of counting factored OV is n squared hard, n squared minus the low of 1 hard. And this is coming from the fact that the counting version of factored OV is sufficiently expressive to capture regular OV, and regular OV is n squared hard from Seth. For factored 0-3 clique, we get n cubed hardness. And first we get hardness from all pair-shortest paths in threesome. And that's through the fact that, counting factored 0-3 clique solves regular 0-3 clique, and 0-3 clique is hard from all pair-shortest paths in threesome from prior work. Additionally, this expressiveness that I mentioned, where there's some sense of universality that these factored problems have, allows us to use counting factored 0-3 clique to solve Seth as well. Basically, it ends up being able to solve the orthogonal vectors problem, and this allows us to get hardness from Seth. I won't talk about how that works in this talk, but roughly these factored problems really are quite hard. And a nice fact about factored 0-3 clique, factored 0 triangle here is that it's a new candidate hard from everything problem, right? Like if any one of our core hypotheses is true, then we get this n cubed hardness. So,
Sorry, Andrea, I have a question.
Yes.
In the previous slide, when you say like sharp FOV is hard.
Oh, here, okay. Yeah.
This is in the worst case?
So this is in the worst case. It's also in the average case because we have a worst case to average case reduction. So the average case of sharp FOV is still n squared hard up to subpolynomial factors, as long as it has a sufficiently high success probability. And here, we can once again think of that as 1 minus 1 over, n to the epsilon for some small epsilon, if you prefer, or you can actually sort of drill down, and it turns out we can get the degree down to omega of 1. And so any success probability of the form 1 minus 1 over some function that is larger than log n, like something that's like log n to the omega 1, so like substantially larger than log n, but like anything that's bigger than a polylog is going to be sufficient to imply a faster algorithm in the worst case, given a fast algorithm in the uniform average case for these problems. And the same is true for the 0-3 clique problem. So we're sort of relying on the fact that we've constructed these nice low degree polynomials, and the fact that we have this framework that turns low degree polynomials into average case hardness.
I see. But this framework, we haven't talked about this yet, or?
I haven't explained how we get the framework, but I gave the sort of theorem statement of the framework. I'm in fact not going to prove the framework in this talk. Yeah, so does that answer your question?
Yes.
Okay, cool. So, here's a question. What are these factored problems good for anyway, right? Like we've just explained a sort of really complicated thing. It would be really nice if we instead didn't have to use these, right? Like why can't we just be back in orthogonal vectors land? And the answer is average case reductions. So if we want to show some graph problem or string problem is hard on average, we can use the average case hardness of these counting factored problems, these sharp factored problems. And the reason that we can use them is that they have these factored problems have a lot of the same structure as their non-factored alternatives. They're still combinatorial. They, in some sense, are the same problem except compressed. So as long as you can sort of handle representing that compression within your problem, then you'll be fine. And to sort of demonstrate this, I'm going to walk through an example of how we like handle specifically that compression step in a particular graph problem reduction. So for the counting version of K node labeled ST connectivity specifically. So what is this problem? You're given a directed acyclic graph with n nodes and m edges. And nodes are colored from some set of colors C. And edges only exist between nodes of different colors. And given the input, we want to count the number of paths from S to T that only use K colors, mod some reasonably large number. And the reason we're doing this mod some reasonably large number is we don't want to potentially need to keep around in our registers like a number of size 2 to the n. So we're doing this mod a number so that we can like get nice, small, easy to work with numbers to handle. So let's consider what happens with 2 colors and this particular graph. Well, we can go through and look at different sets of 2 colors. So with red and yellow, there is in fact a path from S to T. With blue and gray, there is in fact a path from S to T. And that's in fact it. Like if you're limiting yourself to 2 colors, only those 2 paths go from S to T. So our count would be 2 because all other paths are broken. So what can we say about this problem? If C is the number of colors and E is the number of edges, there exists an algorithm that runs in ignoring subpolynomial factors. This tilde is suppressing subpolynomial factors. That runs in number of colors to the K plus number of colors to the K minus 2 times number of edges time. And this is really just a naive guess and count algorithm. You like guess the colors that are going to make your path from S to T. And once you've done this, you're left with an uncolored DAG. You sort of delete all other nodes. You're left with an uncolored DAG that has some number of edges, and you simply, run a counting algorithm, which only takes O of the number of edges that remain time. And the reason that you get this savings of number of colors minus 2 is that every edge can only appear in graphs where those colors are chosen on its endpoints. So, what about a lower bound? What we get for the lower bound is, once again, ignoring these subpolynomial factors and exactly matching running time. And this is coming from the counting version of factored zero K-clique. And note, of course, that we have average case hardness for this problem of the counting version of factored zero K-clique. So I'm going to work through a high level of how this reduction works for the zero triangle problem, our favorite. So, we're given some 3 partite graph. We're going to tag each edge with a factored vector. And we want to sum over all the 3 cliques in this graph, the circ operator run over the tagged factored vectors. So, in some sense, the count of the, if you uncompress it, the count of the number of zero sums. So what we're going to do is we're going to take our factored zero K-clique instance, and we're going to turn it into a graph with S and T on the 2 sides. And we're going to create 1 gadget for each set. And here's the high level structure we're going to want. We want it to be the case that once I restrict to some particular set of colors, where each color is going to correspond to some node in the original. Once I've selected a set of colors, I want there to be a number of paths in each gadget that correspond to the circ operator run over the corresponding vectors. So, the vector that is on the edge between orange and dark green, for example, in set 1. So I want this, the count of the number of the paths to have this property that it's counting the appropriate value. And then I also want it to be the case that in order to get from S to T, I can select any choice of 1 path from each region in order to get from S to T. And as a result, the number of paths from S to T is going to be the multiplication of the number of paths in part 1, the number of paths in part 2, the number of paths in part 3, etc. And so when we're thinking about how does this overall structure capture our sum of our multiplication of our sum, as long as the number of paths internally in each section, in fact, are measuring this green value. So like for given set J, like given set 1, I want the number of paths through region 1 to in fact count this green value for set 1. As long as we have that property, we're then multiplying as we move through the graph the values that we're hoping to multiply. We're in fact getting this purple pie sort of by the structure of the graph itself. And the summation is coming over the fact that we get to choose over all possible choice of colors, which correspond to all possible choices of triangles in the original. So over this entire sum, we then get, in fact, like the sum between S and T is going to be this value of our output. And what does this say for the lower bound? Well, we're going to be putting these nodes in, and each color is representing a node in the original. And each gadget is, as I mentioned, representing some set in the factored vector. And I'll tell you that each gadget roughly has a number of edges that correspond to the number of edges in the original graph. And so what we get is that the number of colors is n, and the number of edges is up to a subpolynomial factor that I'm suppressing. There's one edge for each edge in the original, so we get n squared edges. And this means that if we have an n node graph with n squared edges, and we believe that this problem is n cubed hard, as we do from all of our favorite hypotheses, it implies that there's an n cubed hardness of this 3 node labeled ST connectivity problem. And we can reframe that hardness as either the number of colors cubed or the number of colors times the number of edges. And notably, this exactly matches the algorithm. The last note I want to make is about this average case hardness. If the counting version of factored 0-3 clique is hard on average, as it is in its uniform average case, you can then say that the counting version of 3 node labeled ST connectivity is hard over this distribution that is generated by running this reduction starting from an average case. So you get an average case distribution for this graph problem and for any problem that you have a reduction from, but it's not necessarily the uniform distribution. In fact, in this case, it definitely won't be. You sort of roughly have a gadgety superstructure and then various edges that either exist or don't with probability half IID. So we're sort of roughly like create a superstructure and then tag various edges as random is what ends up happening within this context. There are a lot of reductions we present in the paper, and I don't have time for all of them. And I'm gonna sort of describe at a high level what to grab from this diagram. So in blue, I have all the core hypotheses of fine grained complexity. And in red, I have the clique problem we care about, 0K clique. And in purple, I have our factored problems. And we move from worst case hardness of our favorite fine grained hypotheses into the worst case hardness of these factored problems, which of course, implies hardness for their counting versions in the worst case. And the hardness of the counting versions as a worst case implies hardness of their average case versions via, the good low degree polynomials that exist and our functions. In like double circled, we have various problems for which we get average case hard distributions. And this is edge node labeled ST connectivity, node labeled ST connectivity, and partition matching triangle. There's some problems that we were able to sort of show that factored problems show hardness, but only in the worst case because the counting reductions don't work. Those were all graph problems. We can also sort of get this level of expressiveness from various string problems. Notably, I mentioned at the beginning of the talk that counting the number of regular expression matches, you can show hard. And you can specifically show it hard through the average case counting version of factored orthogonal vectors. We can show worst case tight hardness for KLCS and at a distance also from these factored versions. We can in fact show average case hardness, but it's not tight. So KLCS, the best algorithms take n to the k time. We can show average case hardness of n to the k minus 1, but we don't sort of highlight that here because it's not tight. The rest of these results are tight upper and lower bounds. So what are the results that we cover? So first, there's a framework built on the sort of framework implicit in BBB19. Next, we generate this new type of problem, this factored problem. And finally, using the framework, factored problems, and reductions, we're able to show hardness for a variety of string and graph problems. And we're able to show hardness for some particular graph problem, as we mentioned, this 3 no-label elastic connectivity, from all pair shortest paths, 3-sum, and Seth. And additionally, we have this new hard from everything problem. The counting version of factored zero triangle is hard from all pair shortest paths, 3-sum, and Seth. So if any one of those hypotheses is true, we get that n-cubed hardness we desire. And we get it on average. So this candidate problem has the advantage that if you can build reductions from it, not only do you get that hardness from all of your favorite core hypotheses of fine-grained complexity, you also get a distribution over which you can say that problem is hard on average. There are some things I didn't mention in this talk. Both are explanations or apologies in some sense for why we don't have good low degree polynomials for counting orthogonal vectors and counting zero K-clique. For counting orthogonal vectors, it turns out there exists a fast algorithm for counting orthogonal vectors in the uniform average case. If you had a good low degree polynomial, you would in fact violate Seth. So assuming you believe Seth, you shouldn't hope to find a good low degree polynomial for counting OV. For zero K-clique, it's not quite as straightforward. However, we get a counting to detection algorithm for this average case of zero K-clique. And this doesn't work in the worst case. And there's sort of good reasons to believe that you shouldn't be able to get a good low degree polynomial, because you'd then be able to say something about the detection version being hard, and counting, like getting a reduction in the worst case from counting to detection doesn't seem very plausible. So this sort of presents a barrier to these versions. And why might we care about that? Well, it presents a justification for why we're using these complicated problems, right? Why are we using factored problems? It's because the problems we initially cared about, we can't actually generate these good low degree polynomials for them. Finally, as mentioned previously, you can of course use this framework to show average case hardness for counting any small subgraph, not in an error-disjointed graph, not just K-cliques. I'd like to highlight some recent work in the same area. I'll do it really quickly, but there's this lovely paper by Hirahara and Shimizu where, I kept mentioning through the talk this relatively high probability of success that we needed, right? 1 - 1 over log n to the d, which, is going to be something like a super polylog value in many cases. Hirahara and Shimizu use some really interesting techniques to get that probability a lot lower. And they additionally present a really nice reduction from orthogonal vectors to the problem of bicliques. Oded Goldreich also has a paper out where he presents the results that already existed in BBB. I think Oded's version is like a slightly more efficient reduction, but mostly it's just sort of a different presentation of the same results, which is that in the worst case and average case, it's not just that counting K-cliques are the same, it's also that counting K-cliques mod 2 is the same. So this like potentially like easier seeming problem is also hard on average. Any questions?
Well, thanks, Andrea. I have a question. Do you know, is there like a big difference here in like fine-grained complexity and talking about exact computation versus approximate computation? And would the average case just be easy in the average case, in approximate?
Yeah, that's a great question. So in the worst case, there are many problems, notably the diameter problem in graphs, but also some others, where people have nice results about how hard approximation is. In the average case, all of these reductions rely like on the numbers being exactly right. And it's like pretty brittle to small changes. So we don't really handle approximations very well. For multiplicative approximations, many of these problems are just easy. However, you could it's not clear for K-clique, for example. If we take, for example, square root the number of, or quarter root or something, the number of cliques that we expect, and we ask for an additive approximation of plus or minus a quarter of the square roots that we expect. That problem still seems like it should be hard to me. Obviously, with sufficiently large values, you start getting to the point where you can just say you just say the mean and then you throw up your hands and you're done. But with sufficiently narrow values and a sufficiently high success probability that you're asking for, I think this should still be hard. However, I don't think the current techniques show that. So that's sort of the space in which I think that is an interesting open problem.
I see. And there, the approximation that you would hope is depends on the distribution of the values on this average. Okay.
Yeah, the distribution of the number of K-cliques you expect in a graph is going to look sort of like a binomial around some mean. There's of course some correlations that exist there, but especially for small k, it's pretty weak. It's probably fine, So I think mostly you just don't want it to be the case that you ask for an approximation so wide that the concentration suggests that you can just say the mean of that distribution. But I think especially if you imagine really small additive approximations, plus or minus 10, for example, or plus or minus log n. For sufficiently small approximations, you can deal with the fact that we don't actually make that many queries. And then you can just say well, I know that it has to be plus or minus 1 or something. And so I can simply plug into this algorithm, all possible exact values that it could have been. So you get that range in which you can still sort of use these techniques in a sort of silly way. If you move beyond that range, then it's not really clear what happens, but I think it's still pretty clearly hard for a large section of that range, where I'm not sure what an algorithm would be doing to get an advantage over what we already have, if that makes sense.
There's another question in the chat by Alper and Ergur, who's asking if this framework can be used to prove hardness for planted problems, like the planted clique, for instance.
Yeah, so it's a great question. Unfortunately, the answer is no. We would love for it to be true. Let me rephrase that. If you could find a good low degree polynomial for a problem where you're looking for a single witness, it's like the existence problem, then this framework totally works for that. However, we don't actually have examples of problems where we have good low degree polynomials and they're not counting problems. So I guess it depends on exactly what you mean. There's some sense in which the framework can handle planted problems, but given that we have no examples of that working, I feel like it would be dishonest of me to tell you that that works. Roughly, the counting versions end up being a lot easier to get low degree polynomials for, because if you want something that returns a 1 only when there's a single solution, you need to get agreement across all possible witnesses roughly that only one of them is saying yes, right? Whereas when you do these summations, you get to have nice low degree things, and you don't need to coordinate in some sense across all your witnesses that you're only returning 1 for one of them. Anyway, so unfortunate answer is we haven't been able to find good low degree polynomials for any such problem. But that would definitely, if such a thing existed, it would be very exciting. You'd be able to solve an open problem in fine-grained cryptography that's been open since that 2017 paper of BRSV, where they asked for fine-grained one-way functions. And they gave, a particular definition, and we don't have any fine-grained one-way functions starting from orthogonal vectors, three-sum, or all pair shortest paths as the hardness assumption that you start with.
Cool. Are there any other questions? Or else we can thank Andrea again. And yeah, I can take us offline.